For this section of problems, we're still going to be looking at chapter 14, except in previous we looked at some low pass and high pass filters, but now we're going to be looking at bandpass and bandpass or band reject filters. So bandpass and band reject are going to be the next couple of problems. This one specifically is bandpass, and it's a specific type of bandpass. So you have band passes that are in series and that are in parallel. The next video will be about a band pass in series, and that can be found in the playlist linked below the like button. But this one's going to be focusing on parallel. Now, we have a parallel RLC function. We have our resistor, we have our L, which is the inductor, and then the C for capacitor. So we have these three things which form an RLC circuit, and because these are in parallel with each other, it makes it parallel. So we are going to solve for all of these different things right here. Now, this is heavily formula based, and these formulas can be found in the notes linked below the like button on about page 119. And so it's important to first build the actual voltage divider for this. That's super important because it's just important to understand it. To build the voltage divider, we would need to combine these two impedances together. We will call it R0, and we know that there's some voltage across this. And then we would say that, well, our H of S is equal to a V0 over V input. And we know the voltage divider is V0 is equal to V input times the R0 with the R0 over our, what would be the 300 ohm resistor. We're not going to be focusing on that here. That's just important to note. What we are going to be focusing are on the formulas that are in the notes below the like button. And actually further looking into this, even though it's not important to this problem, we can find our R0. Now our R0 is going to be equal to 1 over the first impedance, so the inductor. Remember that when we need to convert this to the S domain as well. So this is going to be Z of L, and it's equal to a S times our L. And then this is a Z of C, and this is going to be 1 over S times C. So in here we're going to have 1 over S times L, and then we are going to have plus S times C, and this is to the negative first power. So if we were to write this, we're going to have S times L divided by our 1 plus S times C, and then we have our S times L. So rewriting this again, we're going to have S over L, and then we're going to have 1 plus S squared times C times L. Now this would have to plug into here. And I'm going to plug this in and come back to it at the end of the video, because the most important part, again, is the actual formulas from the notes. So to find omega naught, we're also note that we're going to solve for in kilorads. We're going to have the square root of 1 over our L times our C. Now we're going to plug this in as 1 over the 40 times 10 to the negative 6th times 25 to the 10 to the negative 9. And if we do this, we're going to get approximately 1,000 kilorads. Remember, kilo is what we have, what we're going to get from this, which is going to be some huge number, approximately 1, 2, 3, 4, 5, 6 zeros. And then if we have the K, this is rads per sec, and we're going to multiply this by 1K over 10 cubed. So we're going to move this over 3, which will end it to be right here, giving us 1,000. Now, for frequency F0, we know that omega is equal to 2 pi f. So we're just going to plug in 1,000 divided by 2 pi for f, and this is going to give us 159 kilohertz. Now, to find Q, what we're going to do is, well, we can find it two ways. We can find it with W naught or omega naught over our beta, or we can say that it's equal to the square root over R squared times C times L. Now, since we don't have our beta yet, we're not going to use this one, we're going to use this one. And then if we do this, we're going to get approximately 7.5. Now, for omega C1, this can be found, again, in the notes. The derivation of it's not in the notes, but the actual formula for it is. Our omega C1 is equal to the negative 1 over our 2 RC plus the square root of 1 over 2 rc to the squared plus 1 over r times c. And the only difference between this and our omega c1 is that in our omega c1, or I'm sorry, in our omega c2, we are going to replace the 1 right there to be omega c2, and we're going to change this to be a positive. So after we plug all of these in and we convert it to kilorads, remember that's important, kilorads for these, we're going to get approximately 936 and 10,069. To find our beta now, our beta is, we can find it again two ways. We have omega c2 minus omega c1, or we can just have 1 over r times c, and this is going to give us approximately 133 kilorads per second. And that's how you go about solving for this problem. Now, if we were plugging it, looking back here, this is just side note, we've done the entire problem. We would have h of s is equal to our s times l over our 1 plus s squared times cl divided by sl over 1 plus s squared times cl, and then we have a plus 300. And then from here, we're going to multiply everything by this right here, and we're going to get h of s is equal to, we'll have an s times l divided by s times c plus 300, and then we have 1 plus s squared cl. And then from here, we can just do a few things. First, we're going to change this to be in the j omega domain, and this is equal to a j omega times l divided by a j omega times c plus 300, and then we have this s squared, and j omega being plugged into here is going to actually give us a negative 300. So we'll have 300 minus 300 times r omega squared times c times l. And then from here, we are going to see that we have this imaginary part plus the 0 magnitude, so we can write 0 plus j omega l, with this being the imaginary and this being the real. Remember, we have h j omega still is equal to this, and this is all over, again, the real, so whatever doesn't have a j in it, this is going to be the 300, and I'm just going to factor the 300 out again just to keep it simple. 1 minus omega squared cl, this is the real, and then we have plus the j omega times r c, and this is our imaginary. And then we can divide it out, get the magnitude, get the polar form, rectangular form, whatever have you, but that's just a side note of how it would look. And we would also transform this into the standard form for the transfer function. And the transfer function, if it's in the h of s, is basically, well, we have this s times l, so we're going to write this down here. Basic form is s times l is going to be k times our beta times s divided by our s squared plus beta times s plus our omega naught squared. And that's from the notes also, I'm not going to touch on that. The main thing was just that we get this part down. And that's the end of this problem.